Electrochemical machining, or ECM, is a way of machining a part without actually having any contact between the tool and the workpiece. The workpiece is charged positively, as you can see, and the tool is charged negatively. And between the two pieces there is a tiny gap where they don't actually touch, but there is a electrolyte fluid between the two that slowly removes atoms. And as the tool is slowly moved down towards the workpiece, more and more atoms are removed until the workpiece conforms to the same shape as the tool. This is convenient because there is no actual contact, so there's no tool wear and no friction, which causes heat. This can be used for a variety of parts in many complicated shapes, such as this cylinder that has been machined with a sphere. And this can also be used for tiny parts.
For electrochemical machining, or ECM for short, MTU employs two different machining processes. What both have in common is the absence of contact between the tool and the workpiece. Instead, the ablation principle is based on the anodic dissolution of metal during electrolysis. The techniques are used, for example, in the manufacturing of three-dimensional blisk blades out of nickel-base alloys. In contrast to conventional ECM, precise electrochemical machining, or PECM for short, is capable of machining components to near net shape. Exact measurement of the component ensures outstanding manufacturing quality.
Electron discharge machining, also known as spark erosion, uses a graphite or copper electrode placed in an electrolytic bath of water or oil. The electrode discharges a spark that strikes the tool wall. This area reaches melting temperature but is then cooled by the liquid bath, resulting in a thermal shock that causes the metal to fragment into tiny particles, which are then flushed away. All of this happens in a small fraction of a second. Spark erosion works on hard and soft metals alike and can produce very tight tolerances. It's ideal for making deep, thin slots, sharp concave corners, debossed lettering and other features that would otherwise be hard or impossible to machine conventionally. Also, a very fine and smooth finish can be achieved, which eliminates time-consuming and expensive hand polishing.
Electron beam welding is an advanced method for joining metal parts. The electron beam welding machine consists of two main sections, electronics and physical section. The physical section consists of the vacuum working chamber with the pumping system, the manipulator and the electron gun as the electron beam source. One part of the electronic section is a high voltage power supply to accelerate the electrons. The welded parts are placed in the working chamber and the inner space is evacuated. The electron beam is focused onto the surface of the welded workpiece and the weld is formed by mutual movement. Welding is usually performed without any additional material. The combination of the deflection system and the computer can be used to display the workpiece in the electron microscope mode, to weld along complex paths, or to create seemingly multiple beams for multi-pool welding. The The deflection system is also used for engraving and local heat treatment of the surface layer, or in 3D printing using selective melting. A typical feature of electron beam welding is so-called deep penetration effect. Power density of the electron beam reaches such values that the beam penetrates the material very rapidly. Thanks to this, the weld acquires its typical knife-like shape, even for very deep welds. Vacuum as a protective atmosphere, the depth effect, welding of high-temperature materials and reactive metals, and high productivity predetermine electron beam welding for applications in nuclear and automotive industries, in aeronautics and space exploration. The Institute uses electron beam welding in construction of vacuum and cryogenic systems for research projects. Under the contracted research, the technology is available to 50 cooperating industrial partners as well.